Otherwise, if that's not the case, then you can get 2 to the 1 mapping, and that is, by definition, is not injective. I've talked about many times. So let's try two examples of this. So I know G1, H1. Not working. Let's go down here. So f of G1, H1 equals f of G2, H2. Right? So we're trying to show that G1, H1 is equal to G2, H2. Right? That these 2 points are effectively the same in the domain. Right? Well, what is this? So you just swap them around. So this will be H1, G1. Okay, same logic here. So this is H2, G2. Okay. Now these are the same element. So that means H1 equals H2, and G1 equals G2. And that means that H2, G2 is equal to H1, G1. Okay? So that proves injective. Now, again, we can use the size thing, size argument. Right? What's the order of this group? Right? Well, it's the order of G times the order of H. So if that's order M, that's order N. The order of the direct product is M times N. And a similar argument here. So the order of this is N. The order of this one is M. Right? So the order of the direct product is N times M. And the order of this product is M times N. Well, Mn equals Nm. So the 2 orders of these are the same. And we have proven injectivity, the size of the 2 sets or groups are the same, and therefore that theorem, therefore if size is the same and injective, therefore the mapping F is surjective. So if it's injective and it's surjective, it's bijective. Alright? So we've proved it's bijective. Now we have to prove the FMN thing. So how to do that? So yeah, we have to do this again. This form. Now M in this case, this M and N, what are they? They are elements of a direct product. Okay, so let's say x1, y1. So some binary operator x2, y2, right? And we have to show that is of that form. So let's see. So we can rewrite that. Now, the definition of a binary operation of a direct product, remember, it's that by that, comma, that by that. Okay? Remember the definition of the binary operation, the product, if you like, of 2 elements of a direct product group. So it's that by that. So this will be f of x1, x2 dot y1, y2. Alright? Now what does f do? It just swaps them around. So this will become y1, y2, comma, x1, x2, right? Now, now we can do the reverse. Now, what we did here to get that, we can do the reverse on this to get something like that, right? So, we just do the opposite. Right, so what is this? Now this is the product of two elements of a direct product. So we can rewrite this as y1, comma, x1, binary operator, y2, comma, x2. Okay, so if you want to go back, if you multiply, you form the binary operation of two elements of a direct product group. You get y1, y2 here, comma, x1, x2. That's the definition of your binary operation of a direct product group. Right? If you're rusty, go back to products of groups lecture chapter. All right. Okay. So what is this? Well, this is f of x1, y1, right? And this is f of x2, y2. Right. And there it is. Okay. So this is of that form. So like mn, and then you get f of m, f of n. So we've done it. All right. So that's proved 9. Okay, 13. Prove that if G is cyclic and G and H are isomorphic, then H is cyclic. Okay. So you've got two isomorphic groups, G and H. You know that G is cyclic, so prove that H is cyclic. How do you go about doing that? All right, well, there's probably various ways. Here's one. Okay, cyclic. So any cyclic group has a generator. Okay. So was this question 13? We have some space. I hope this shows up. Okay, so question 13. So G and H are isomorphic. G is cyclic. Prove H is cyclic. So G is cyclic, it has a generator, and the order of that element, the generator, little g if you like, is the order of the group. Okay, so the order of the group, the size of it, now that has to equal the order of the other group, because we're told they are isomorphic. And let that order, the size of the group, let it be, I don't know, n, let's say, right? So, so I'm using here the result that the order of the element that is the generator, that order, the number, is equal to the size of the group. Okay, so let G be the generator of G. So G to the m is e to G, right? Now, if I now try to calculate, let H be a member of big H, and let me try to calculate this. Right? Now, if this works out to be e to the h, if this works out to be the unit of h, right, with the same m, that means H is the generator, little h is the generator of big H. Follow that? Or do you want me to say that again? Okay. The G and H are isomorphic. Therefore, their sizes, their order, the group order is the same. Okay? And let that order be n. Now, little